Have you ever done a science experiment and wondered what it'd be like if you did it big? I have.
Yeah!
My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, Experiments at Large. Science Max!
Science!
Today's Science Max is all about balance.
Okay.
If it's a potato or if it's me, figuring out how things balance is what we're all about.
It works really well!
Swinging, spinning, and staying put. Today on Science Max Experiments at Large.
Greetings, Science Maximites. Today, we're gonna be talking about, balance, or what you call balance in science, which is center of gravity. Now, the center of gravity is a place you can find in any object where it's equally balanced on all sides. I balanced this spoon on the eraser of this pencil, and where the spoon is balancing is its center of gravity. But if I take this little tiny dime and put it in the spoon, it doesn't balance anymore. But if I put the dime in this spoon and balance it in a different spot, I can find the new center of gravity, and the spoon balances again. Here's another experiment you can do. Take a potato and a ruler or a stick. Try to balance the potato on the ruler. I'm gonna save us both a lot of time. It's really hard to do. The potato does have a center of gravity, but because of its shape, it's going to be really hard to find and really hard to balance. But if you take some forks and you stick them into the potato, you're no longer just trying to balance the potato, you have to balance the forks and the potato. And it gives it a very different center of gravity, which makes it a little bit easier to find and a little bit easier to balance. Ha-ha!
Whoa! Let's take a closer look at how the center of gravity works. Using our potato. No, that's too close. Back off a little bit. Okay, good. If you want to find where the center of gravity is, you can hang an object and draw a line straight down. Then hang it from a different spot and draw another line. Do this 1 or 2 more times and you can see where the lines meet is the center of gravity. If our potato was balanced on a stick, the center of gravity is a long way from the stick, so it's going to be pretty hard to balance. Now, let's stick some forks in the potato and try again. One line there, a line there, and a line there, and you can see that the lines all come together down here. That's right, the center of gravity doesn't have to be on the object. With the center of gravity way down there, when we try to balance the potato and the forks on the stick, you can see the center of gravity is much closer to the stick. That makes it way easier to balance.
Now, because you're Science Maximites, I'm sure you know that a potato and forks is just the beginning. Everything you have in your house has a center of gravity, which means, theoretically, you can balance anything. Try it yourself. Find things around the house and see if you can get them to balance. And if you can't, try adding things to increase the center of gravity and make it a little bit easier. Now we're gonna max it out. That's why I'm gonna go to the Center for Skills Development and Training, and we're gonna explore center of gravity even more. See if we can get something to balance. And what better thing to balance than me? Oh, table, right. Hey, this is Sandhya and Swapna. No, Sandhya and Swapna.
Right.
And they are going for their PhDs in science. And you guys, thank you for coming.
Thank you.
Work with Let's Talk Science, right?
That's right.
All about science education, just like us. And I'm glad you guys are here because I need to max out this. Oh, look at it balance. Whoa. Hey, whoa. Okay, I got it, it's fine.
Good. So we're gonna get a gigantic potato?
No, I thought we would use me instead.
So you're the potato.
Yeah, I guess I'm the potato. All right. And I need something to balance on.
Well, how about a tightrope?
Oh yeah, a tightrope. Have either of you done a tightrope before?
Nope.
Me neither. All right, let's set one up.
All right.
Okay, good. Yeah, it's great.
We're gonna take our balancing potato experiment and max it out. To get a potato to balance is pretty hard, but if you stick forks in the potato, it works a lot better. In our maxed out version, we're gonna balance on a slack line, which is sort of like a tightrope. It's a flat strap tightened between 2 points. And in this version, I'm the potato. And instead of sticking giant forks in me, which is not something I want to try, Sandia, Swapna, and I are going to experiment to see what I can do to improve my balance.
There. We're using this ratchet strap above a crash mat because we only have it about 3 feet off the ground, but it's still gonna be really hard to balance on, right?
Right.
Okay, so who gets to go first? Okay, here we go. Ready? Hey.
Got it?
No. No. Okay.
I think what you need to do is spread your mass out more to be able to find that center of gravity easier.
So I should balance on one leg?
Start by trying to put your arms out.
Let's
Good
try
call.
this again.
Trying it again. All right.
All right, arms out.
Okay.
Let's see if this works.
Okay, so when I say, you're gonna let go. Ready?
All right.
1, 2, 3, go. No!
It's a little bit better.
It was a little bit better.
a little longer.
That I went from 1 second to 3 seconds. Yeah!
Yes.
I would like to actually take 1 step.
Okay.
That would be nice.
Well,
What else can we do?
maybe we can try weights. Try and hold them out.
If I have weights in my hands, that would increase the center of gravity in terms of putting
Putting it
the
in.
weight on the outside. You guys have something we can use?
Sure, yeah.
actually.
Okay, good. Wow, these are heavy. Okay.
These are weights.
Yes, they are. Well, that's what they're for. They're supposed to be heavy. Good call. When I hold this one, and I'll borrow your shoulder, Swabna, and then when I say, Sandia, pass me the other weight. Here we go. Ready? And pass me the weight. Oh, no. Okay, that didn't work. Okay, good. Whoa. Okay, let go. Okay, let go. Oh, no. Oh, it's really hard. I feel I would work better if I could lift the
Yeah.
weights up, but they're too heavy for that.
All right.
So what else can we do?
Well, tightrope walkers use a long pole so that they can balance on a tightrope.
That's right, I've seen that. Do we have a pole?
We
I
can
think
go
we
find
can.
one.
Okay, great. I'll put the weights away. Have you ever heard someone say, I will be back in a jiffy? Well, now you can tell them that's almost impossible. You see, a jiffy is an actual measure of time. It's 1/100th of a second. You see this timer? The first number is seconds. The second number is tenths of a second. And that third number that you can't even read, it's going so fast, that's hundredths of a second. Each one of those is a jiffy. Here are some things that happen in a jiffy. A cheetah moving top speed travels 20 centimeters. A hummingbird flaps its wings almost once. Can you blink in a jiffy? Nope, takes 10 jiffies for that. How about snapping your fingers? 8 jiffies. So the next time someone tells you, I'll be back in a jiffy, you can tell them it took 170 jiffies just to say that. So I tried walking the slack line, and I wasn't very good at it. Holding my arms out at my sides seemed to help a little. Then I tried holding some weights to see if that would make any difference, and the weights were so heavy, I couldn't really hold them out very far. Now the plan is to try a long pole. Tightrope walkers use long poles to help them balance. The longer the pole is, the more it affects your center of gravity, especially because you can move it up and down to help you stay balanced.
Ta-da!
Nice. So the important thing on this is what? The balance, right?
Yeah, you
That's
want to
right.
find the center of gravity of that as well.
So
you
try
can
and find the center of the
balance
pole.
it.
The center is right there. That's where it balances.
There, you got it.
Okay. How do I
Okay.
hold this and get up on the strap?
I'll help
You're
you.
gonna help me? Okay. Oh, okay. Uh-huh. Whoa. Whoa.
You good?
Okay. I think I got it.
Okay,
Yeah. Whoa.
you're balancing.
Check it out. Hey, this isn't so bad.
Hey, look at that.
You can really use it to help correct when you start to fall. You just move the pole, and that's totally helping my center of gravity stay right in the center above the strap. Whoa.
You can do it.
A long pole can help tightrope walkers and me balance in two ways. First, it lowers my center of gravity. Normally, a person's center of gravity is about here, but with a pole, it changes to way down here, much lower to the thing I'm walking on. But a long pole also helps in another way, because in order to fall off the rope, I have to rotate. It's easier to rotate something that has mass in the middle than it is when the mass is spread out. That's why you put your arms out when you want to balance. A pole works just like your arms. The mass gets spread out way more, and it makes it much harder to rotate around the rope and fall off.
There you go. Center of gravity. We're done. Usually we don't have it figured out this quickly. Usually we struggle a little bit more. All right, high fives.
Way
we did
to
it.
go.
Way
Awesome.
to go. So we did it.
Yeah.
We achieved what we set out to do, balanced with a pole. So how else can we use science to make my balance better?
Well, tops are great because when they're spinning, they balance.
That's right. So the forces used when something spins is something I can use.
Yeah.
All right, this calls for another small experiment. Are you guys good here?
Yeah, sure. We'll keep practicing.
Awesome. All right, back to the lab.
Bye, Phil.
Here's another experiment that's all about balance. Take a pencil and try to balance it on its tip. Doesn't work that well, does it? But if you take a pencil and stick it through a circle of cardboard and try it again, it works. The reason is because this circle is spinning, it creates a force that keeps the pencil standing up. As long as the circle is spinning fast enough, it counteracts the force of gravity because of the conservation of angular momentum. The conservation of angular momentum. The conservation of angular momentum.
Science Max presents Ways to Sound Super Smart. A top will balance when it's spinning. It works because it spins. But why say it that way when you can impress your friends and all the adults you know by saying conservation of angular momentum? Why does a top spin? Because of the conservation of angular momentum. Between you and me, we know that it boils down to the fact that it's spinning. But conservation of angular momentum is how you say it if you're studying physics in university. Just remember to thank Science Max when you impress everyone by telling them a top balances because of, say it with me, the conservation of angular momentum.
Now, let's max this out. Gyroscopic force is pretty amazing. Because this bike tire is spinning, it's hard for me to move it. But it's really hard to see how much it resists a change in orientation unless I do this. Ha ha ha! It looks like it's defying gravity, but really it's because the amount of force needed to change its orientation is more than the force of gravity pulling down on it. It won't last forever, only as long as the bike tire keeps spinning. But you gotta admit, it's pretty cool science. And whoa! Science! Look at that, it totally balances.
Yeah.
So this is a great way to balance. Do you think it'll work if I hold it?
Well, let's see you try.
All right.
right.
So I'm gonna use you to get up on the thing, and then you go, give her. Yeah, that's good. And spinning it up. Here we go.
Ready?
Yep.
Okay.
Yeah. Whoa. You can feel it. I can really feel it resisting, and
Yeah.
I think it would work.
I think it just needs to be spinning a lot faster.
That would make even stronger. Yeah. It kind of hit my chest, so.
You know what? Maybe you should keep it out to one side.
Well, it's still spinning, yeah.
Well, won't that?
I think you need two.
Oh yeah, you're right, one on either side. It'd be great if we could actually have some way I can keep my arms free though.
Yeah.
Oh, I know. Get two wheels and we rope them into some sort of backpack situation.
What?
And we have a way for you guys to get the wheels spinning really fast.
I don't know.
No, I have it all in my head. Trust me, come on, I'll show you. I'll show you. Wait, you guys go around. Come, don't go on that side of the. Time for a mini-max. Here's how you can use the forces of things spinning around to defy gravity. Well, sort of. Take a ping pong ball and put it in a plastic container like a cup, or this is the top of a CD spindle. Put it in and start spinning it around. If you do it right, you can get the ball spinning only on the sides of your container and not touching the bottom. That's centripetal force at work. Oh. It works a lot better, and it's much more impressive if you have something that doesn't have a bottom. Fortunately, I do. This bucket doesn't have a bottom. Put the ping pong ball in the bucket and spin it around, and if I'm very careful, I can lift the bucket into the air and ta-da! I'm defying the force of gravity. Science! Now I know what you're thinking. You're thinking, Phil, is that it? Is that all you're gonna do? No, of course not. This is Science Max Experiments at Large. This is a garbage can with no bottom in it. And this is a bag of golf balls. Let's see what happens when we put them together. Well, I managed to keep one golf ball in my garbage can. But as you can see, it works really well. And there you go, sort of maxed out. This is a garbage can with the bottom cut out, and this is a soccer ball. I'm gonna see if I can keep the soccer ball inside the garbage can using centripetal force. Okay. It's working! It's very tiring, though. How do you throw out a garbage can that's been used? Science! Here's a fun experiment you can do that plays with the forces created when you spin something. Get a flat platform or a tray and tie rope to every corner. Get an adult to help you with this. Then you get a cup of water. Use a plastic cup, definitely, just in case. You put it on the tray and you start spinning. Now, the forces created when you spin something, centripetal force, pulls the water to the outside of the circle. And because the centripetal force is stronger than the force of gravity, no water spills out of the cup, even when it's upside down. If you slow it down very carefully, you'll see that all the water is still in your cup. Now, I definitely suggest you do this experiment outside, and I definitely suggest you do it with an adult. Because when you get tired, which you will, if you don't stop it carefully, you'll have to explain what you've been doing. Science!
Using science to improve my balance has totally worked so far. So now, Sandia, Swapna, and I are trying to figure out how to use the forces created when a wheel spins to help me balance. We need a spinning wheel on one side and one on the other. I've decided to take 2 bikes and remove the handlebars, seats, and front wheels, then cross them over each other and attach them to a backpack. Sandy and Swapna can use the pedals to spin the tires fast, and I will use the gyroscopic force to balance. Or at least, that's the plan.
Behold, the Gyroscopic Stabilization backpack! Stabilization away! I'm excited. Okay, you think it's gonna work?
I think so. I'm kind of skeptical.
Really? You're skeptical? Why?
I don't know. I don't know if you can do it.
I don't know if I can do it either, but that's why we do science!
Let's see it.
Okay, spin me up. Okay. Oh,
Ready?
yeah.
All right.
And, oh, Ready? Go.
Yep.
Oh, yeah. It's working.
Cool.
It's working.
It's actually working.
That's good. Oh, it's getting harder. It's getting harder.
Uh-oh.
Whoa. That worked really well until the wheels stopped spinning.
Yeah.
And then what happened?
Well, when the wheel was spinning, it was resisting motion in all directions so that you wouldn't fall.
Yeah, but when they stopped spinning,
You didn't have that anymore.
that doesn't do anything. It's just a 50-pound weight on my back.
Yeah.
Exactly.
Right. So I guess that's why tightrope walkers don't use spinning wheels. They use a pole instead.
Right.
But we've proven that they can.
Exactly.
Yeah. Max out, high five.
Yeah.
Woohoo! Yeah! I now have the balance of a ninja circus performer thanks to...
Science!
Thanks for watching Science Max Experiments at Large. Okay, spin me up. Spin me up. And we'll do some more science. Gyroscopic backpack to the rescue. All right, let's go.
Science Max is a show where we take small experiments and do them big. If you want to try these experiments yourself, go to our website for instructions. But not all the experiments on Science Max are the kind you should try at home. This one, yes. This, no. Try this, don't try this. A big yes, a big no. I don't know how you could possibly do this one at home. And remember, if you're ever not sure, ask an adult. Thanks for watching Science Max Experiments at Large.
We should put fans on them and I can fly. Now, I know what you're thinking. You're thinking, why didn't that work? And the reason is because I didn't do it right. I got 2 turntables and no microphone. I am defying. Come back here, spin it around, and spin it around, spin it around, and spin it.
Have you ever done a science experiment and wondered what it'd be like if you did it big? I have. My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, Experiments at Large. Science Max! Today, I'm maxing out the power of water. Water is very heavy. Pressurizing water to make a water-powered car, water pressure pumpkin carving, water flying, and more. All on this episode of Science Max Experiments at Large.
Greetings, Science Maximites. Welcome to Science Max Experiments at Large. My name is Phil, and today we're gonna be looking at water. But water is very heavy, but that's okay because we need it to be heavy for this experiment to work. I don't know if I need that much of it though. Maybe I can get, here we go. Yeah, that's probably all I need. Today, we're going to be building a water-powered car.
You'll need a base for your car, like this styrofoam, water bottles, shish kebab skewers, straws, scissors, elastics, paper plates, tape, a square of paper towel, modeling clay, vinegar, baking soda, water, and glue or a hot glue gun if you have an adult to help you, and... yeah, I know, this one is pretty involved. That's why you should go to the website for step-by-step instructions. Take your paper plates and glue 2 together to make a wheel. Then make 3 more. Wrap elastics around your base and then tape straws on the bottom.
Trim them down, maybe about that much.
Then take your shish kebab skewers and push it through a water bottle cap to make a hole. Then stick 1 wheel on, put the skewer through the straw, and
Do the same thing on the other 3 sides.
then take the water bottle cap and get an adult to help you make a perfect hole in it so that it fits your straw. Then use some modeling clay and hot glue to seal the straw and the cap so it's airtight. Attach the water bottle to the base of your car, then fill it with some water and vinegar. Next, you'll want to wrap up a spoonful of baking soda in the square of paper towel so you can make a little package. Finally, stick something underneath the underside of the bottle to raise the end up off the base.
Bring your cap and then go outside. here we are outside. Yeah, I know, we're not really outside, but I have a science lab, and you probably don't, so I highly recommend you do this outside. And don't forget your safety glasses. Now, this is why we make a little packet of baking soda, because we want to delay this reaction as long as we can. So I like to hold it there. We'll hold it there with one finger so I can get the cap ready, because we don't want it to react until we can get the cap on, and then kink the straw to keep the pressure inside till we're ready to let it go. Then, at the last second, you want to drop that packet in and quickly cap it, and kink the straw, and woohoo! Woohoo! There you go, a water-powered car. Now, I know what you're thinking. You're thinking, Phil, wait a minute, that's a vinegar and baking soda-powered car. Well, kind of. The vinegar and baking soda create a gas, and that gas creates pressure in the bottle, and that pressure forces the water out of the bottle. But it's the water leaving the bottle that creates the thrust. The water going that way pushes the car that way. Newton's third law, every action has an equal and opposite reaction. So what we're gonna do is max out the water-powered car. Figure out how to get water going that way so we can go that way. But we means me and someone else. Who can help me? Oh, I know, Anthony from the Ontario Science Centre. He'd be great at this. Hopefully he's not busy. We're gonna max out the water-powered car. Ha. Anthony!
Phil!
Sorry about that. Did I scare you?
Don't worry about it.
How you doing?
Awesome, thanks.
Great. I was wondering if I could get your help on an experiment.
Yeah, okay. Which one?
I'm building a water-powered car. It's gonna be great. It's Science and Max headquarters. I'll show you.
Phil?
Anthony, I'm here.
Whoa, Phil, where are we?
Oh, this is the parking lot for Science Max headquarters. So,
Okay.
today,
Yeah.
I want to max out the water car.
This thing is awesome.
Yeah, so what you do is you use vinegar and baking soda,
Yeah.
and you pressurize this container, and,
Okay.
and the water shoots out that way. So the car goes this way.
Newton's third law. Every action has an equal and opposite reaction.
Yeah, you know your
Okay,
stuff. This
okay.
is why you're here. This is because I could really use your help and advice on how to make this bigger.
Okay, so we're gonna need a bigger tank to pressurize. So this, what about something like this?
So we need something that can hold pressure. Do you think this would work?
I don't know if we'd wanna...
And we'd have to put like pressure fittings on the barrel, like cut a hole
Yeah.
and weld them on. I don't know if that's...
Something tells me this wouldn't work, so we
Okay,
need,
sure. I got some other stuff over there maybe that we could use.
Check this out. Yeah, I think this would work. This would work a lot better.
Well, this is my stand-up wash tub base.
Your what?
So
Yeah.
we'll reuse it. Yeah?
Okay, you know what I'm thinking
Yeah.
now, though? I know
Yeah.
this. The problem is, I think this is like an oil drum, right?
It is.
And,
It's an oil tank from a house.
and these things are not built for pressure.
You can get water tanks that you pressurize.
Like hot water heaters, yeah, you can pressurize. They're built for that stuff. You pressurize them in your basement, and then the water travels up to like
the top
your
floor.
shower
That
or
makes,
something like that.
So all we need to do is get a pressurized water tank,
Okay.
put water in it, put pressure in it, and put it on wheels. And then we open the valve and it goes, right?
That sounds amazing.
All
yeah,
right.
let's get to it, man. Okay. we
I got
need
some water tanks over here in this corner of the parking lot.
Seriously?
Being a chef is my absolute passion. And cooking up science recipes is my speciality. I'm Buster Beaker, and this is Cooking with Science.
Oh, hello. When you're a professional chef like me, you spend lots of time perfecting the perfect recipes. I know my way around a kitchen, and today I'd like to show you one... That's not the fridge. Oh. Today I'd like to show you one of my favorites. Quail truffle gazpacho cakes on a plate of ice. Beautiful. And here's how to make it. Take some quail, some truffle, and some gazpacho and put it into a cake. Delicious. And here's the interesting part. How to make the plate of ice. Ooh, how did I do it? Well, I tried many different methods, and none were very successful. But now I let science do the work for me. So here's what I do. You see, I've got my large block of ice, and I've got a fishing line over the top, and on the bottom, I've got 2 heavy weights. Now we wait.
The heavy weights put pressure on the fishing line. This pressure melts the ice where it's pressing down. As the ice melts, the fishing line moves through the block of ice and eventually cuts its way through.
There we are. My hours of waiting have almost paid off. You see, I've got a perfect line through the ice, and I stopped it just before it finished. It's the pressure of the line on the ice that makes it work. The same thing happens when you use ice skates. You see, it's a very thin line, and your body weight presses down on the ice, melts it a bit, and that allows you to glide across the ice. It also allows me to just pop this off. There you are, you see? Perfect plate of ice to put my delicacy on. Let's just try that now. There we
So I've joined Anthony and we're going to max out our water-powered car. Our small design works by creating gas, which creates pressure, which forces the water out of the bottle, creating thrust. Our new plan is to get a water tank, put it on wheels, and put water in it. Then we use an air compressor to pressurize the air inside. When we open the valve, the water is forced out this way, which causes our water car to go that way.
Okay. Ha-ha! So, water car, maxed out version,
Huge.
water tank.
And filled with lots of water and lots of air. Too. Yeah. Pretty good, right?
Whoa.
It's a lot of it. So,
Did it mess up my hair?
no, you look fine. You look great.
Okay, good.
Now, the only thing left is we just gotta open this valve here, right?
Yeah. You want to do the honors?
Yeah, let's do it, okay.
Okay, here we go. 3,
2,
1, go!
We open the valve and our pressurized tank moves forward. The air pressure in the tank forces the water out with enough force to move the tank.
Awesome! That was awesome!
That was a great run, yeah.
That was amazing.
So, pressurized water tank on wheels.
Totally worked.
Totally works.
Total success, yeah.
So, because this is Science Max, the only thing we can do now is make it bigger.
Bigger,
right?
exactly,
Okay.
yeah.
So, problem is,
I don't think we're gonna find a tank bigger than this one.
Yeah.
So,
because then it would be too heavy, right?
exactly,
Much
way
bigger.
too heavy. Maybe what we can do is just get a lot more water,
Okay.
and then we find a way to pressurize the water.
Oh, so don't pressurize the whole tank, just the stream of water that's going out
As
of
it
the tank.
comes out, exactly. Something kind of like a fire hose.
A fire hose, right.
So
we take a big container of water,
right?
and I guess we would need a pump.
Yeah, like a pump would be perfect.
So then we suck the water out of the container, put it through the pump to pressurize it, shoot it out of a fire hose.
And then our car goes flying.
Goes flying.
Okay.
Yeah, let's do it.
Yeah.
All right.
Amazing.
When water is going fast, it has a lot of force. This is a power washer. It's made for cleaning concrete and wooden decks, but it doesn't use soap and it doesn't use heat. It only uses the power of water. Let's try it out. The power washer creates a stream of water that is moving really fast. It has the force to clean concrete, strip the paint, or even the Science Max logo off wood. But how do I max out the power washer? What's the most ultimate use I can think of? Power washer pumpkin carving! The power of the pressure washer creates a stream of water strong enough to make short work of my pumpkin. Power washers may only shoot water, but they can be dangerous, so don't try this at home. Yeah, science!
The Wizard Academy. All you have to do is demonstrate true magic, and you'll be granted entry.
Send in the next candidate. Oh, no, not Overwhelmo.
Did someone say Overwhelmo?
Wait, no. Next. No, not that. Okay, good. Okay. Behold, it is I, Overwhelmo!
Welcome back, Overwhelmo. If you can truly demonstrate magic, you may join the Wizard Academy.
A glass of water! No, wait, that is not the whole trick. Okay, hold on. Okay, and this, a waterproof playing card. I put the card on the glass and flip it upside down, and then I say the magic word. The magic word. And behold, magic! Yes?
Is that it?
Yes?
Well, it's not magic.
It is defying gravity!
Nope,
The water would fall and the card would fall to the floor.
it's not magic.
This is magic!
No, it's science.
Horse feathers!
Look, the reason the water doesn't come out is the air at the top of the glass keeps it held in by suction. More air would have to get into this glass to decrease the suction, and because the playing card is keeping a seal on the glass, the suction of the air is holding the weight of the water up.
Balderdash!
All right, look, let's do a little experiment then, shall we? Let's move the playing card just a little bit from the edge of the glass. You see those bubbles?
Yes?
That's bad news. Science, not magic.
Well, I will return, and then you will see your mind will be melted by the. No, that's not my music. Hold. You will rue the day when. That's not my new. Hold. Overwhelmo shall return.
Our maxed out water car worked pretty well. Now it's time for something even more maxed out. We start with a giant tank on wheels, we add a pump to pressurize the water, and a fire hose to shoot it out the back. What's more, this version is big enough for me and Anthony to ride.
Water car! Amazing!
Is the more super improved water car. This tank holds 1,000 liters, and right now it has 720 liters of water.
We have a pump. That's right, our water pump. So the idea is we take the water from this container out through your hose, really pressurized, going really fast that way. Our car goes really fast this way.
All we gotta do is just turn on the pump, and we're ready to go.
So we fire up the pump and the water stream comes out really strong. So strong I can barely hold on to it.
Here we go!
But even so, there's a problem.
What's going on back there? I got it! Yeah.
Nothing happened.
No, nothing really. Well, something happened. We got wet, but it didn't really.
It's too heavy.
Too heavy.
So you're on it and I'm on it. That's a lot of weight. We don't ride it. That's something.
Yeah.
Also, this is kind of going crazy.
Yeah, because if nobody's holding it, it's just gonna flap around.
So we'll have a brace here.
yeah.
Shoots it that way. That's good.
And then we'll need, I feel like we'll need something to kind of propel it. Maybe a better propulsion system. Kind of like one of those steamboats.
So we put a big paddle wheel here.
Exactly.
And we aim it, I guess we aim it down
at the, yeah, exactly.
like that
And then,
at the paddle wheel, and then the paddle wheel spins, and that propels the car,
exactly.
right?
Right.
Okay.
Okay, well,
We can do that. Let's do it.
sounds good,
Put it
yeah.
together. You know what? I have a paddle wheel because I had a failed hydroelectric.
This is called flyboarding. Wow. Whoa. Powerful jets of water are being shot out from this board at my feet. Whoa.
The engine on the watercraft behind me creates the water pressure, which travels up the hose and through the jets. The force of the water is strong enough that I can use it to fly around. So what's the difference between this and a water car? Well,
We don't have to take that much water with us because it starts in the lake and ends up in the lake. so the only water I have to carry is in the hose that goes up to the platform. Woo-hoo!
Flyboarding is lots of fun, but it takes some practice to get it right. Balancing on jets of water isn't easy, but I got the hang of it.
It's all due to Newton's third law. For every action, there's an equal and opposite reaction. Physics! Woohoo!
Our maxed out water car didn't work so well. The main reason is that much water is heavy, 720 kilograms.
Yeah.
So Anthony and I have a plan. Rather than rely on the force of the water going straight out the hose, we're gonna put a water wheel on the back of the water car. A water wheel works by catching water in the segments of the wheel. The weight of the water on one side of the wheel causes it to start turning. But we're gonna use the weight of the water and the pressure of the water. Hopefully, both combined will be enough force to turn the wheel, which will drive our water car forward. A little construction, and we have it ready to go. Okay, so here's the latest version of the water car, water wheel!
Yeah.
All right.
Yeah, there we go.
We try it out, but there's a problem. The trick with the water car is the water itself weighs a lot. Every liter is 1 kilogram, so our 720 liters we start with is way too heavy to get the car moving in the beginning. But as the water gets pumped out, there's a sweet spot where the weight is low enough the water car might move. But then there's only a little water left, so it's a balancing act. We fill it again and see if we can come up with a plan. Okay, new and improved version, only half full. So the idea this time is because we're starting with it only half full, right?
Yeah.
Then it'll begin to go a little easier because it won't have as much weight as it had the last time we did it. And Phil, yeah?
I can't even move this thing.
What?
I think there's too much fuel. There's too much. Yeah, there's no way we can move this. There's no way this is gonna be able to move
Even
on its own.
half full, you
Even
can't
half full,
move
I
it.
think we need less fuel than we gotta get down to like maybe like a quarter or something like that.
The thing is, we ran it from the full tank last time, and it never
Okay.
moved at all.
What if we gave it like a push to kind of help it get over that little bump of energy?
Ah,
Oh,
so give it the first push when it's still got a bunch of water in it. We give it a bit of a push, and then maybe it'll go in its own.
Exactly.
Okay.
Wanna get it
Yeah.
down?
Absolutely. Let's do it. We start the pump and wait for the amount of water to get to just the right spot. Then we give it a push while it's still kind of heavy to start it moving. Sure enough, that push makes all the difference.
Yeah,
The water car is light enough to roll, has some momentum to keep it going, and the force of the water coming out the pump is enough to keep it moving forward on its own.
Still going! Woo-hoo-hoo! All right!
amazing! Yeah! Look at it, man. This thing worked like a beauty.
It worked out. It went all the way.
Yeah!
Way to go. The water car, finally a success. It was the push.
It was the push. That's all we needed to get it going.
A bit of a push to get it going and a lot less water, and there you go. It totally works. All right, you want to do it again?
Absolutely.
All right, here we go.
Okay.
See you next time on Science Max Experiments at Large.
So much easier to push it without any water inside it.
Ah! Let it go and
There we go. Oh, careful.
I can't really see with my goggles.
Behold the power of physics!
Yeah.
The door's off.
This is called foot. Whoa!
All we have to do is wait. Have you ever done a science experiment and wondered what it'd be like if you did it big? I have. My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, Experiments at Large. Science Max! We're flying again on Science Max.
Gliding squirrel.
Throwing things, spinning things, tumbling things, and maxing things out just a little too much.
Go, go, go! Go, go! Wait!
Keeping things up in the air is what's on the runway for this episode of Science Max, Experiments at Large. Well, hello there, Science Maximites. Today, we're going to be flying on Science Max Experiments at Large. Take a look at this. It's my paper airplane. Give her a bit of a throw and she flies amazing. Now, take a look at this. This one is lighter than air. It's a helium balloon, and guess what? It flies on its own. See you later. Well, just hold on a second there, friend. What's this whatchamacallit called? I'll tell you. It's called a hoop glider. Give it a toss and she flies really well. But today we're flying in a whole new way, Science Maximites. I know it sounds like we've covered all the bases for flying, but we haven't. Come on, follow me. Oh, didn't actually realize how much these goggles would fog up. Where was I? Oh, right, we're flying today on Science Max. Come on. Today, we're going to be building a tumble wing. That's a kind of paper airplane that flies on a cushion of air. This is a big mouth tumble wing. It doesn't look like much because, well, it's not. It's just 2 strips of paper taped at either end. But what you do is you throw it in the air and you walk along behind it with a hard surface like this, and that little scoop of air keeps it flying. And here's how you can make a tumble wing of your own. But first, a word about paper. Did you know that paper comes in different weights? The kind of paper you get from the printer is actually pretty heavy. The ideal paper to use for tumble wing making is from a phone book. You may not have a phone book at home. They're kind of rare right now, but its paper is very, very thin and the perfect for tumble wing flying. Now, if you don't have a phone book around, you can use newspaper. It works almost as well. What you do is you cut out some strips of paper, and you just need 2, and you put them on top of each other, and then you offset them, which means you take the top one and you slide it over till there's about maybe a centimeter, 2 centimeters, something like that. And then you take your handy dandy science tape, which is the same as regular tape, except you use this tape only for science, and you tape the edges very carefully like that, and flip it over to the other side. Make a little tape on this side, just like that, and there you go. You have a big mouth tumble wing. Now you also want to tweak it just like you do with a paper airplane. You want to curl the paper a little bit, curl this side a little bit, and let's see how it flies. You'll know you have it right when it doesn't go to the left or right, but just opens up and tumbles straight down. Ah, not too bad. That one curved a little bit, so I'll have to tweak it a little more. Now, the other thing you're gonna need is a nice hard surface. The kind of signs that you get when there's an election are perfect. I happen to have a few of these sitting around, and they are made of something called corrugated plastic. They're very light, but they're also very hard. So you can use this, but you can also use cardboard if you don't have any of these around. So what you wanna do is get your tumble wing and your hard surface and flip it in the air, get it flying very nicely, and then walk behind it with your board, and a scoop of air will be behind it, and it will fly. But it may look easy when I do it, but that's because I've been practicing quite a bit. So here are some tips for tumble wing flying.
Tumble wing flying tips. When flying your tumble wing, you want to be indoors, away from any wind or other kinds of moving air. A long hallway or a big room is best so you don't run out of space. The angle you hold your board is important. Too much tilt or too little and it won't work. Keeping your tumble wing in the air is mostly about the speed that you walk. Too fast and the tumble wing will go over the top. Too slow and it'll fall. Finally, practice, practice, practice. Happy tumble wing flying!
Now I just need an expert to help me. Okay, let's see here. Lisa from Logic's Academy. She'd be perfect. Okay. And, oh wait, I need a lab coat. Oh, and Lisa needs a lab coat. There we go, Lisa's lab coat. Good, my lab coat. All right, my turn. Oh, my lab coat changed color again. I'll fix it later. Lisa's gonna be here any minute.
Oh!
Hey!
That was so fun!
Oh, did you like the portal?
I loved it, hi, Phil!
Lisa from Logic's Academy, I'm glad you're here. Your lab coat changed color as well, though. It's supposed to be yellow. I think we had a glitch.
I kind of like it, though, blue.
No, but we gotta do yellow. Yellow is the Science Max lab coat color.
Okay.
So, we are here to talk about the tumble wing. I've got my big mouth tumble wing here.
I have
Got
mine,
yours?
too, yeah.
Now, what are we want to max it out, obviously. What else can we do?
Well, actually, there's a lot of different designs that we could try. This is a big mouth tumble wing. There's also tumble wings that are just a straight sort of single wing.
Oh.
And then there's some that are like an actual airplane or a glider.
Ooh, and we can max them all out.
Of course.
All right, let's get started.
Let's do it.
And we'll get the yellow lab coats.
And I really like the blue.
We gotta get the yellow on. There, now we've got our yellow lab coats. I've got my big mouth tumble wing, and I got my board to push the air.
Oh, look at that! I voted for you.
You did?
I did.
Oh, you were the one. Okay, so let's talk about the science going on behind this air surfer.
Okay, so just like in an ocean, if you were surfing in an ocean, you'd be surfing on a wave of water. Right now, our tumble wing is surfing on a wave of air that you're creating with a board. And air and water are actually both fluids.
Oh, cool. So
they
we can
behave the same way.
So it really is surfing.
It is surfing. And actually, sometimes we call those air surfers.
Cool. Well, why don't we have a surfing competition? Because I actually have here a Team Phil board and a Team Lisa board. Okay, so what do you want to have a race?
Yeah, absolutely.
Okay, you want to take this one? This one flies really well.
Definitely.
I'll make a new one.
Okay.
Welcome to the Air Surfing World Finals, almost live from Science Max headquarters. I'm Jim and I'm joined by Chuck. Today it's Team Phil versus Team Lisa.
Team Lisa has a lot of heart, Jim.
But Team Phil is on his home turf. Let's see how they do. Round one is, of course, the tumble wing race.
And a great day for air surfing. The teams are ready, and there they go.
Ooh, Team Lisa looks like she had some trouble starting. Team Phil has already pulled ahead, but Team Lisa is off the marks now.
I think that beginning fumble might have cost her.
Let's see. Team Phil with a commanding lead, but Team Lisa's catching up. Oh, Team Phil loses his tumble wing at the last minute. A great dodge and a pass by Team Lisa. Can she hold it? And no!
Taking 10 steps back is the rule when you drop your tumble wing, Jim. It's anybody's game.
Looks like Team Lisa fumbles her start. Phil pulls ahead. Can he be caught?
Almost at the finish.
Yes. Team Phil with the win. What an upset.
All right, you had a lot of practice with that one.
Yeah, okay, so you got another design?
Yeah, let's try the single wing
New
one.
design.
Okay.
So at the end of the first round, we have Team Phil with 1 point, Team Lisa with 0.
But now we go to the second round where the design changes. We're now looking at a single wing design. It still tumbles like the big mouth tumble wing, but made from a single wing.
Does that make them harder or easier to fly, Chuck?
A bit harder. They're faster and more maneuverable.
If you wanted to, you could research tumble wing and you would be able to find this design. And this is what these show you where to fold it.
Yes. So the dotted lines or the dashed lines are where you would fold, and the solid lines is where you would cut.
What's more, Team Lisa has more practice with this version.
And they're off. Oh, Team Phil with another early lead, but Team Lisa's catching up.
Phil doesn't have much practice with this version, and it's starting to show.
You're right, Phil fumbles. Oh, Phil fumbles, and Lisa passes him for the win. There we go. At the break, we're all tied up with Team Phil and Team Lisa with 1 point each.
Look how well mine's going. This is an ornithopter. It's a machine that flies by flapping its wings. When people were still trying to figure out how to get something to fly, they thought, copy a bird. A bird flaps its wings and it flies, just like this. So, why don't we have airplanes that fly by flapping their wings? It turns out that flapping wings is actually complicated mechanically. First of all, you have to tilt the wing when you go up so it doesn't take as much air, and then turn it so you push more air on the downstroke. So flying like this would be kind of hard for an airplane and really hard to do on a large scale. So humans came up with this, a propeller. A propeller catches the air, and if you spin it fast enough, it gives you lift. So if you orient it upwards like a helicopter, it will give you lift, or if you orient it this way, it will give you thrust, just like an airplane. So that begs the question, why don't birds and insects use propellers to fly? Turns out, though, that rotating a propeller is really hard to do with something that has muscles and tendons. So in the end, birds fly by flapping their wings, and humans first learned to fly by rotating a propeller. Science.
Lisa and I are air surfing. We've tried 2 different versions of tumble wings, but now Lisa has a new design, one that doesn't spin as it flies.
Okay, so what do you have now?
Oh, check this out, Phil. This is a Mosquito glider.
All right, so it's like a paper airplane.
Yeah, but it's not made of paper. It's made of a light foam.
Ooh.
The Mosquito gliders work the same way as the Tumblewings, but because they're much larger, they're much harder to control.
I got it. Oh, no, 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 no. Oh, almost into the stuff. Not bad though, right?
You got it.
This is very tiring.
This is really hard. It takes a lot of flying time to master.
We got the hang of it, but we quickly learned that you have to run a lot faster with the gliders. And we were soon out of breath.
Oh, sorry. You gotta be in good shape for this.
Turns out a bigger glider is much harder to fly. So,
Ultra maxed out Mosquito glider.
we made it even bigger. Why? Well, because it's Science Max.
Bigger board.
We needed a much larger board and tried first with 2 people.
Ready? Going. Oh.
And then with 1. And the most we were able to get it to fly was not a lot. Our conclusion?
Large airplanes just don't fly very well.
Well, homemade ones.
But we can try something else.
Okay,
Let's try something else.
let's try something else.
Today only, I got a super special on anything that can fly. Go on, pick something out. Oh, you had the paper airplane. Oh, good choice. Good choice. But guess what? Paper airplanes don't fly. Full price. Yeah, I know, but before you start arguing with me, you need to know the difference between flying and gliding. A paper airplane does not fly, it glides. You need constant thrust in order to fly. If you do not have constant thrust, then you glide. Take this bird. This bird can fly because it flaps its wings. It has constant thrust. On sale. But this airplane cannot fly. You give it some initial thrust when you throw it, but after that, it can only glide. Full price. But look at this. It's an airplane powered by a propeller on an elastic. Now we're talking constant thrust. It can fly. On sale. But it can get confusing. I mean, look at this flying fish. Nope. Flying fish cannot fly. They can only glide. Full price. Look at this. It's a cute little flying squirrel. He climbs a tree, jumps off from a high branch, opens his legs, and there's a little flap of skin there that allows him to sail to another tree. Haha, flying squirrel. No, not flying, no constant thrust. Gliding squirrel. Full price. Okay, tell you what, you came all the way down here, I'll make you a deal. Check this out. Flying fish, now it has a propeller, it has constant thrust. It flies for real. And ditto, squirrel with a jet engine. And now you know the difference. Something that flies has to have constant thrust. Otherwise, you're just gliding. Squirrel away! I forgot to gas him up. Look at those clouds. Aren't they nice? Did you know there are different names for clouds? Like those clouds right there? Those are cumulus clouds. They're the kinds that look like cotton balls, really fluffy and light. Well, they're not exactly fluffy and light. First of all, they're not fluffy, they're wet. It would be sort of like being a very dense fog, and it'd be very wet if you were in that cloud. And they're also not light. In fact, they're not light at all. That cloud right there weighs about 500,000 kilograms. That's the same as 100 elephants. 100 elephants just floating around in the sky? Come on, how does it do that? It does that because it's so spread out. But water is very heavy. Interesting to think about. 100 elephants just floating around in the sky above our heads at all times. Almost makes you want to go inside.
Our air surfing tumblewings worked well, but our Mosquito gliders were a bit too maxed out to fly really well.
Large airplanes just don't fly very well.
Well, homemade ones.
But maybe we should try maxing out the tumblewing just to see what happens. So we did!
Okay, Lisa, I'm gonna throw it, and then you're gonna push the sign.
What?
Go! Wait.
Oh, did it go? What happened?
It didn't. Whoa! It didn't work.
We tried it and tried it. And it turns out, yeah, it doesn't fly.
Go, 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 go! Go, go, wait.
But I mean, this is science, Max, so of course we had to at least try maxing it out.
Phil,
I don't know if this is working.
it's heavy.
It's very heavy. Okay, maybe we should go back to a slightly smaller version.
Sounds like a plan.
Okay.
High five?
High five. This is a boomerang. Boomerangs are from Australia, and the cool thing about boomerangs is when you throw them, they come back. With practice. That was close. When you throw them, they come back. And it comes back. Comes back. Come back. Come back. So, why does it come back?
Well, if you take a look, it's made of two wings, like airplane wings, but with one important difference. You see, a wing has a shape called an airfoil, and this gives lift. But check it out. The boomerang has one airfoil pointed this way and the other pointed the other way, which means if you spin it in the right direction, each wing will get lift as it rotates. But how does lift make it come back? Well, that's the trick. You see, you throw it sideways. The lift from the wings makes it go in a big circle and come back to you.
So when you throw a boomerang, this side starts to go this way and it gets a little bit of lift. Then this side gets a little bit more lift, and then this side gets lift, and each time it gets lift, it starts to turn just slightly. So as the boomerang spins, it describes a nice big arc in the sky and comes right back to you. Ha-ha! And that's how a boomerang works. Thanks, Phil. No problem, Phil. Hey, do you want to get lunch? Yeah, lunch sounds good. Okay, come on. Well, the Science Max headquarters has a nice cafeteria.
We've tried air surfers of all shapes and sizes. And what have we learned?
Maxing out an air surfer by making it bigger is really difficult.
Very difficult, yeah.
So what we've decided to do is go back to our original big mouth tumble wing and instead do it on a maxed out obstacle course!
Tumbling surfing round 3, the maxed out obstacle course. Let's take a look at the obstacles. The tree slalom, the podium ramp, the hanging hoop, ring walk, wall of boxes, ladder tunnel, side hoop, ball promenade, and the barrel run.
So here's how we play. I go through and then you follow me. And if you make it through an obstacle and your tumblewing's still in the air, you get a point. And at the end, we count how many points we have and we see who won.
And it looks like they're ready to start. Here we go!
Where are you, Team Lisa? Oh. Whoa, yeah. Whoa, no. Okay, what do I do with the boxes? What do I do with the boxes? Going through the boxes! Definitely didn't make that one. Recover! Ah! Oh. Okay, definitely lost a point there.
I'm almost there! Right behind you!
Yeah! Uh-oh! Knock the barrels over, getting
I
through
get
the
an
finish
extra
line.
point for
And Team Lisa! Oh, yeah! Nicely done, high five.
Awesome!
See how the airflow from the board keeps the air surfer in the air? Well, the trick is to give it just the right amount of air to keep it in control. Not too fast and not too slow. That's the science to good tumblewing flying. So, with the points from the last round added up, Team Phil and Team Lisa are tied again!
You know what that means? Tiebreaker! Thanks very much for watching Science Max Experiments at Large Tumblewings. You want to go first
I
this
do,
time?
let's do it.
Okay, you go first this time, and then I'll follow you. I think it's easier to go first. So, okay, ready?
Yeah.
You ready? Set, go. Ah! Sorry, that's very loud.
Yeah.
Whoa! I didn't see you there.
Look at this.
You'll know you've done it right if you... Fixed!